Let's continue to talk about the other useful mathematical tools in QuantLib. Suppose we have a set of sample data for a portfolio on hand, and we are interested in the statistical properties of this portfolio, such as the mean, variance, skewness, covariance, and correlations. Then the sequence statistic class is our choice. Once we create the sequence statistic object, then we can input the portfolio sample data one by one using the add function. And once we have filled in all the sample data, we can then obtain those statistical properties by calling these functions. This is particularly useful when we calculate the portfolio VAR using the model building method by characterizing the portfolio return from the historical data and then obtaining the covariance of the portfolio return. For the details on these implementations, please take a look at my YouTube tutorial part 3 or follow the link here. Besides statistical analysis, another very important aspect in quantitative finance is to perform calibration. For example, we may have a set of market prices for a type of instrument with different maturities. And we have built a mathematical models with a set of coefficient parameters so that we can use the model to price this type of instrument. What we are interested in is to calibrate the coefficients in the risk-neutral world, such that we can exactly price back the market price for the instruments. In QuantLib, we can achieve this calibration task through the optimizer class. There are various kinds of optimizers that we can select, and different kinds of optimizers will have different sets of configurations parameters when we create the object. To perform the calibrations, we also need to formulate the cost functions, either by least square errors or maximum likelihood estimations. The cost function should contain a set of coefficients, and then these coefficients will be calibrated by the optimizers during the minimize operations. One of the examples of the calibrations is to calculate the portfolio VAR by the extreme value theory. This technique employs the maximum likelihood estimations to calculate the parameters betas and c of the general parental distributions for the excess loss modeling. After that, we can use the calibrated model to calculate the portfolio VAR or expected shortfall at higher confidence level. Again, for the details on these implementations, please take a look at my YouTube tutorial part 3 or following the link here. The next mathematical tools that I will introduce is the Interpolation class. In QuantLib, there are various interpolation methods. These methods will base on the given set of x-y pair to be provided in the constructions of the object. For example, suppose we have a set of options with the same maturity but in different strike price. From the observed option price, we can get their corresponding implied volatility. And if we plot the implied volatility against the strike price, its smile shake can be observed, and we call the plot as the volatility smile. What we are interested in is that for those options with different strikes that the prices are not observable in the market for some unknown reasons, then how we could estimate the implied volatility by interpolating between the adjacent observable points. By using the bracket operators, we can obtain the interpolated results easily. Another subject that we may come across frequently is the matrix calculation. To create the matrix object, we should specify the rows and columns of the matrix, or just the size of the vectors if we create the vector object instead. And after the matrix or vector object is created, we may then initialize the elements using the square bracket operators. Where the iterator type represents the pointer to the matrix element in real type. After that, we can perform various kinds of matrix operations. Like transpose of the matrix, determinants of the matrix, inverse of the matrix, and the multiplications of two matrices. The last mathematical tools that I will introduce is the uniform random number generator. There are various kinds of uniform random number generator that can be used. Notice that during the construction of the object, we should initialize the object by a seed. That can be a fixed number if we want to generate the same random sequence every time, or the seed can be a random number through the following function call if we want to generate different random sequence every time. After we create the uniform random number generation object, then we can call up the next function repeatedly to generate the random sequence. That's all about the mathematical tools in QuantLib. Let's do the third exercise. Please go to my YouTube tutorial part 3 for the demonstration of using the sequence statistic class and the optimizer class. The interpolations class example that we have just gone through can be found in this sample code. Here we create the interpolations object with the strike volatility pairs here. Notice that the X component has to be sorted in order to make the interpolation operation work correctly. We can then obtain the interpolated result by calling the blanket functions. The matrix class example that we have just gone through can be found in this sample code. Here we create the matrix object with the initialization done here. After the initializations, we can do various matrix operations by calling the corresponding functions. The RandomNumber class example can be found in this sample code. Here we create different kinds of random number objects with the initialization done by random seed. After we get the random value once, then we initialize the object by another random seed before we generate the next random value for each object. Let's build the code, run it, and compare the result with the example. This result is corresponding to the interpolation example. This result is corresponding to the matrix example. Okay, we have finished the third exercise. Let's continue to talk about the class relating to the interest rate.